Now, let's get back to where we were in week 5. It seems like a long time ago, right? It seems like a very long time ago. So, just let me refresh your memory. We started the section on matrices, and in this course, we do one topic per week, okay? So this week it's matrices, and we started one lecture early, right? So we did an example in week 5, but let me just sort of go through it again. The main ideas are the following. Eigenvalues and eigenvectors, right? So math 1, 2, 3, 1. Diagonalization, math 1, 2, 3, 1, right? Now we're going to take those ideas and apply them to optimization problems and also differential equations, systems of differential equations, okay? So just to refresh everyone's memory, because you know it's easy to forget, when we talk about eigenvalues and eigenvectors, this is the main equation that, that we're talking about, right? And in this setting, v is a vector and lambda is a number, okay? So for those non-zero values that equation holds, we talk about lambda as an eigenvalue and v as the corresponding eigenvector. Okay, so A is just a square matrix here. So that's what you see in first year, and you want to find the lambdas, find the v's, and then somehow diagonalize things. All right, so in this course, the way they've set it up is looking at these quadratic forms, okay, and applying matrices somehow to better understand those quadratic forms. All right? So in first year, and we can go over this again, you learn how to diagonalize a matrix A. So it's a square matrix, and basically when your aim here is to come up with this new matrix where all the eigenvalues are down the main diagonal. Yeah? And you can do that through multiplication. And essentially what you do is you consider P inverse AP, where P is a matrix that involves the eigenvectors as columns, okay? Now, in week 5, we talked about special, very well-behaved, friendly matrices called symmetric matrices, right? So let me give you an example. That's an example of a symmetric matrix, because if you switch the first row with the first column and the second row with the second column, the matrix stays the same. Okay? So, you know, another way to look at it, if you don't like that, just draw a diagonal. Can you see how it's like a line of symmetry? Oh my God, right? It's a line of symmetry. That's really where the word symmetrical matrix comes from, I think, right? So for this nice friendly case, this diagonalization and the inverse matrices and whatnot are the easiest and the friendliest and the simplest, okay? So the way you do it for this nice symmetric case is you compute the eigenvectors, normalize them, so you give them length 1, and then you write them as a column. In that case, the transpose is equal to the inverse of this new matrix, which is nice, right? Because the transpose is super easy to calculate. The inverse is hard, or harder, especially if it's like 3 by 3, 4 by 4, 100 by 100, right? Nobody's got time for that. So in this case, it's sort of like the starter entry to diagonalization and all this sort of stuff. Okay? So Questions so far? Because it was, week 5 seems like a long time ago, right? Questions so far? Does anyone remember this from 1231, Math 1231? Yeah, a little bit. Mama hoo hoo. Yeah.
Is P always symmetric?
No. So the nice thing about P here is that the inverse and the transpose are the same. So if it was symmetric, P inverse would have to be P transpose, right? But it's not. It's not necessarily true. Yeah. So to answer your question, no, but the inverse is symmetric. The inverse of P is symmetric, I think.
Can you explain that X transpose AX thing again that you went over in week 5?
Yes. So exactly that's what we're going to do. Yeah. So with these quadratic forms, you can write this as these products, right? So here you can think of xy as being the transpose of a vector. This square matrix is A, and then you've got a vector here. All right? So given that form, what can we understand about these quadratic forms, x squared plus 3xy plus y squared? Okay? Now note that this matrix here is what? What kind of matrix is it? It's symmetric, right? So that's one thing we're going to take advantage of. Symmetric matrices have nice properties. They lead to certain geometric connections, but the point is the eigenvalues and the eigenvectors are nice and easy. Okay? So let's go through that example that I did in week 5. Yeah? Should we do that? All right. Okay. So some of you will have forgotten this, that's fine. In this situation, we've got this quadratic form, right? X squared minus 4xy plus y squared equals 6. Now, we don't know how to draw that very easily, right? If it was x squared plus y squared equals 6, yeah, sure, no worries, it's an ellipse, right? If it was x squared minus y squared equals 6, hyperbola, yeah? Right? But the thing that gets in the way is this term here, right? That's the problem term, really. And so what we're going to do, we're going to try to manage that term away. We're going to manage it in some way, okay? And I think I said this in week 5. At high school, you probably learnt a method called completing the square. Completing the square. This is just like completing the square, but it's not as easy as completing the square. It's harder, right? If you don't know what completing the square is, look it up. It'll change your life, okay? Almost. All right, so the way I'm going to do is write this left-hand side as the product of these matrices. And then I'm going to get to work on the matrix in the middle. So if you have a look closely, you've got 1 and 1. They go down the main diagonal. And then the other term is halved and written down the other diagonal. Okay? So we've got this form again, x transpose times a times x equals 6. Okay? So we want to diagonalize. Standard method, let's try it and see what happens. Okay? We notice that the transpose of that matrix A is the same as A. So it's a symmetric matrix, right? So if I draw a little diagonal, it's a line of symmetry, right? Above and below. Think of it like a mirror. Okay. So how do we diagonalize a matrix? Think way back to first year. Yeah, you. Get your eigenvalues, get your eigenvectors, and then write your eigenvectors as columns of a matrix, okay? So the only thing that's different here is that I've decided to make these vectors have length 1. That's what the hat means, the little hat, right? So why have I done that? Because if you do that, the inverse will be the transpose, which is easy to calculate. That's the point, okay? So even if you don't care about that, let's go and get the eigenvalues. So you solve the eigenvalues from that determinant equation. And that times that minus that times that, and you get this, and you'll get 2 eigenvalues. Sometimes you'll get repeated eigenvalues, but for the entry-level problems like this, you'll never get repeated eigenvalues, ever. And they'll always be real. Okay? They'll always be real. So, you don't need to think too hard, which is great. Right? Okay, so you get the eigenvalues, lambda equals -1, lambda equals +3, and then you go through and you compute the corresponding eigenvectors. So basically, to get the eigenvectors, you're solving this system here. Okay, and it's a bit fiddly sometimes, but for these problems, it's pretty easy. Okay, so you want to come up with that vector v, which is your eigenvector. So let's go in here, sub in my first eigenvalue. That'll become a you'll get a 1 minus -1 and a 1 minus -1, so 2 down the diagonal. So you get that, and now you've just got to work out the components of v, right? So 2v1 equals 2v2. Basically, both rows tell you that. So you can just choose v1, any v1 and any v2 such that they're equal. Okay? And then I've done an extra step and just normalized it by dividing by the length. Okay? So obviously, if you're going to do that, you probably don't want to choose v1 equals 100 and v2 equals 100, right? Because it's going to make that more complicated. Okay? And then you just go on to the other eigenvalue, right? So lambda equals 3, replace lambda with 3 in there, and you've got this. So this is like the previous one, but not exactly. You're off by a minus sign. So the relationship is v1 equals -v2, so I'll just choose v1 equals 1, and v2's got to be -2, and then I'll normalize it. Okay? If I do that, I'm going to write my eigenvectors as a column. They've got length 1 and they're mutually orthogonal, which is great. So that's true. Okay? All right. Now, let's go back to my quadratic form. I've got this mess over here, and I've boiled it down to this product. Now I can write A as P times D times P inverse, where P inverse and P transpose are the same. Then I can move that around using transpose properties to get this. And now here comes our diagonal matrix, right? So let's have a look at this. Let's have a look at this and see what happens. Okay. So it's a bit of a mess now, and you don't have to do these in the questions. I'm just showing you sort of why it works here. You get this format, and then you kind of can put it all back together again, right? So you've got this mess, you expand it, do the multiplication, do the transpose, and you get this, this, and this. Look, diagonal matrix. If I expand that out, I get these squared characters. Now, can you see in this mess, there's no x times y term? Okay? There's no x times y term. So I've gone from something with squareds and an xy term to something that has just squareds in it. Okay? All right. So what is this then? If I have a form like this, say in y1, y2 plane, it's not going to be an ellipse, it's going to be a hyperbola. Okay? And because these things are rotations, you're not going to change the distance to the origin when you make these change of axes or change of variables. Okay? So, to work out where the closest point is, that was the original question, right? So, determine the points that lie on this curve that are closest to the origin. Okay. Well, I've transformed everything, which is fine. And I get something like this now. Okay, where y1's that, y2's that. Okay. So when is this equal to 6 and what are we going to get here? Well, put in y1 equals 0 and solve for y2. Okay, so I'm going to get y2 equals plus or minus square root of 2. And then I can transfer that back into xy coordinates. That's what I've done. Okay? Now, when you're doing these questions, you wouldn't write all of this down. You would basically find the eigenvalues, find the eigenvectors, and then just write down something squared plus or minus something squared. Okay? You don't need to know the change of variables. I've just put it in there just to show you. Okay, you don't need to know that y1's that and y2's that. You don't need to do that to do the problems. Okay? All right, let me pause there. Questions? Questions? I'll unpack this a bit more. I just want to refresh your memory.
Okay, thanks. Sorry, if you scroll up like a tiny bit, when you're changing, or like when you're subbing in the value for like P transverse, or transpose, whatever it's called, yeah.
Yep.
It's, so the P is it transpose or transpose?
Yeah, P transpose, yeah.
It's the same as just P.
P inverse.
Like, well, if P is 1, 1, 1 minus 1, like up where you've got P equals.
Yeah, so here I've got A equals this, right? Because D equals P inverse AP.
Okay.
So I've just undone it, right? So let me just see if I can write this. So we know that that's true, so A's got to be that, and in our setting, P transpose and P inverse are the same thing. So I can say, hey, that A is that, which is that, right? And then I can just write that in terms of transpose properties. Okay?
So when you sub in the values of P transpose in the bracket, it's the same as the matrix is the same as P. So I was
you can. Yeah. Yeah, so P transpose is P.
Oh, okay, and then you just got X transpose. Oh, okay.
So remember, so if you've got a product and you transpose it, right? You flip the order and you put the little transposers in. So AB all transpose is B transpose times A transpose. Yeah? Yeah, oh, you're grilling me in week 7. But it's good questions. Yeah. Anyway, is everyone having a good April Fool's Day? The number of posts I've seen, right? I was going to do something, but nah, stuff it. I was going to say, like, there's no lab test 2 or something. Anyway, other questions? Any questions at home? Come on, people. How many people are watching online? Oh, it's 19 people at home. What have you been doing for April Fool's Day? Tell me at home. All right, so let's look at this final form a bit more. Okay? So I'm going to go to good old GeoGebra. Okay? Here we go. Start calculator. All right, let's just do 2D. All right. Okay, bear with me, people. All right, so let's have a look. I think I've got it big enough. Okay, so to apply and solve these problems properly, you need to understand the difference between an ellipse and a hyperbola. Okay? So I think we can all recognize ellipses when we see them, but the way I remember it is if the coefficients, like the number in front of all the squares are positive, then it's an ellipse. Okay? It's like a squash circle, right? If you change one of the signs, then it transforms it into a hyperbola, right? So I'll just do that. Okay. So you can see now I've changed one of the signs, and you'd call this a two-branch hyperbola. It's got two branches, right? And it doesn't cut the y-axis. Why doesn't it cut the y-axis? Who can tell me? Who can tell me on this foolingest day of the year? Why doesn't it cut the y-axis? Yes?
If x was 0 to equal 14, y would have to be imaginary.
Yeah. So exactly. So a good test is put in x equals 0 and you get negative 3y squared equals a positive. So the only explanation is imaginary, which we don't care about. Okay? So if we change that a little bit more, let's go over here. What will happen if we do this? Oh, it doesn't like it. Okay? So if I change the signs, then basically you're rotating the graph, right? Okay, so let's get a little bit more difficult. Let's go into the three-dimensional space. Can you believe it? Okay, so the easiest case. Oh, no. I don't know, 21? Okay, so the coefficient on all the squareds are positive. And if we change the sign on some of them, then the surface changes as well. Okay? So let's change one and see what happens. Boom. Yeah. Yeah, it is a bit like a yo-yo, right? So if you look here at the sort of the cross section, it looks like a bit like a hyperbola that we just saw before in 2 dimensions, right? And then if we look down here, it's sort of wrapped around the y-axis. Why is it wrapped around the y-axis? Well, put in z and x equals 0, and you see you get something that's wrong, that doesn't make sense. Okay? So this is called a one-sheet hyperbola. Okay? It's got one bit to it. Okay? So let me show you a two-sheet hyperbola in 3 dimensions. Basically, we change two negative signs. Yeah, look at that. Look at that. Okay? So that is what's called a two-sheet hyperbola. Okay? So the way I remember it is if it's all positive values, 2x squared plus 3y squared plus 5z squared equals a positive value, it's an ellipsoid. Okay? If there's one negative sign, it's the thing I showed you before, which I call a hyperbola with one bit to it. It's all connected. This is the third situation where 2 of the numbers involved, 2 of the coefficients have negative signs. And so you get a 2 sort of branched thing. Okay? Now, you won't have this in lab test 2 or the final. Okay? You won't have it. So you need to remember some ways of, understanding. So, the way I just look at the signs. If they're all positive, it's an ellipse or an ellipsoid. If there's one negative value, it's a hyperbola in 2D or a one-sheet hyperbola in 3D. And this is the third case. 2 negative signs, 2-sheet hyperbola. Questions?
Did you say there's certain values we can sub in to say like what the shape will rotate around, like something to do with zeros?
Yep. So, okay. So let's talk about this very question. Okay. Have a look at the picture. Where is the closest point to the origin on that red surface? Where is it? Like, you don't have to tell me the point, but where is it just about? Where is? Let me rotate a bit. People at home, I'm looking in your direction as well. Where is the closest point to the origin on that red surface? It's about 3, yeah. Right, give or take. And it's on which axis? It's on the x-axis, right? So it'd be about 3, 0, 0, and negative 3, 0, 0, right? Exactly right. Okay? So when you transform all your amazing quadratic forms, be they in 2 dimensions or 3 dimensions, you're going to get something like this. You'll either get this, or the previous picture, or the ellipsoid. Okay? The closest points will always be on one of the axes. Let me say that again. The closest point to the origin will always be on one of the axes. Okay? You just need to know what the surface looks like generally, and then how to find the closest point. Okay? It's not hard, but it can be quite visual, and students go, oh, I can't even graph like y equals x squared. How can I do this? I get it. In some of the questions, the graphs are given to you. Have you seen this? Right? So let me show you. Let me go in here. Oh, by the way, quiz 6 and quiz 7, which isn't available yet, they have the same due date. Okay? They have the same due date. It's because of week 6, basically. Okay? So... Oh yeah. Okay, all right, so here we go. So here's one I've done earlier. This is a classic engineering maths question. Okay, I'll put this up on both screens. Okay, so it's a surface in 3D space, and you want to write it in the form, x transpose A times x. Okay? Now, not quite sure how to do that yet, but I will show you. The thing I want to concentrate on is the conclusion. Okay? They claim that you can get it down to there, which is nice. Thank you, Mobius, for telling me that. So, looking at this, what surface is it? What kind of surface? Is it an ellipsoid, a one-sheet hyperbola, or a two-sheet hyperbola? 2 sheets, exactly. Right? So it'll look like the previous picture that I put up. Okay, so what do? Set that equal to 0, set that equal to 0, and rearrange and solve for x. Okay? Easy. Yep. And then they've even got some pictures. What's that? Ellipsoid, one-sheet hyperbola, two-sheet hyperbola. There's only 3 options, right? There's only three options. So even if you guess, you've still got 33.33% chance of, getting it. All right, so back here. Let's just go up here for a second. How do you actually get this form for the three-dimensional case? I'm glad you asked. Okay, I'm glad you asked. Well, let me look at what's down here. So the coefficients of the squareds are just down the main diagonal. So that, und that, they go down the main diagonal. Okay? And then these other ones down the other diagonals are half of that coefficient, und that coefficient, und that coefficient. So that's the xy, that's the the xz, and those two down there are the yz. Okay? So, if you're ever unsure, you can always do the multiplication, but nobody wants to do that, let's be honest.
How come we have those coefficients in the diagonals? How come we have those coefficients outside the diagonals?
Well, because when you do the expansion, so why is it half? Okay, if you do the expansion for this setup, because you've got two of these things, right, two of the x's basically, if you don't have the half, you'll get twice more than you need. So just do an expansion and see. So yeah. Okay, so down the main diagonal is easy. This is half of the xy coefficient, so that one. This is half of the xz coefficient, and this is half of the yz. And of course, you want it to be symmetric. So why do we like symmetry? Because it saves us time, right? It saves us time. We only have to compute some of the values. We get the other ones for free. How good's that on an April Fool's Day? All right, let's see what's happening at home. Oh, come on, there's 21 people. What's going on? Nobody's like, is anybody alive? Hello. Oh, here we go. Someone in Ainsworth for April Fools got honey and spread it all over the stairs on the floor, and so that it was dripping down the handrails too, was literally everywhere. Naughty, naughty. Anyway, thanks for sharing. All right, so questions. Questions. I almost guarantee you'll get something like this for lab test 2. I almost guarantee it. Okay? That's pretty much on the bank of questions. Okay, you don't need to know the format, the actual change of variables. You just need to know that it's going to lead to something like that. Okay? Which you're asked to do something with. Okay? All right. Okay, so let me just write this out a little bit more carefully, because this is helpful. So let's say I have something like this.
We can't see what you're writing.
Oh, hang on. The big reveal. Thank you for telling me. All right, so A, B, C, D, E, F are all constants. They might be positive, they might be negative. Okay? If you want to write this in this form, okay? So A, C, F down the main diagonal, and then half of that coefficient down there, half of that coefficient down there, half of that coefficient down there. Sorry. There. That's right. Is that right? Yeah. Okay. Now remember, we're looking for it to have symmetry down the main diagonal. So you'll know if you've made a mistake. Okay? Okay, so for these three-dimensional cases, the method is the same as the previous one example that I went through. Find the eigenvalues, find the eigenvectors. There'll be 3 eigenvalues, 3 eigenvectors. Okay? Once you've got that, you know that you can write it as the sum of squares involving the eigenvalues. Okay, so you know that you can write it. Where are you? Yeah. Like this. Right? Yeah, okay. So, if you're in 3-dimensional space, not 2-dimensional space, you'll just have a sum of these squares. Okay? Now, the lambda 1s may or may not be positive. If they're all positive, you know it's an ellipse or an ellipsoid. If some of them are positive and some of them are negative, it's a hyperbola or a hyperboloid. 1 sheet or 2 sheets, depending on how many negative signs you got.
Just looking at that equation, right? That only includes eigenvalues. Is there a reason to search up find the eigenvectors at any point?
If you want to find, so the eigenvalues, the eigenvectors for your problems are not so important, but you do want to. You can compute the eigenvectors because they'll point along the change of axes. So when you change variables, you're changing the axes, right? You're rotating the axes. The eigenvectors will point in the direction of those new axes. So you have one like that, one like that. Yeah, but we wouldn't ask you to do it. Yeah. Other questions? Other questions? Okay, 3-dimensional space is very, very, very similar. And I'll probably do an example, or I guess I just did an example for you on Mobius. So, okay. Yeah. All right. What else is happening at home? All right. Other questions? I will do some more examples, so don't worry. Okay. Just give me a sec. Oh, yes. All right, so. Let's do something involving 3 by 3. Okay, so this is from Quiz 6 Mobius. Okay, so I thought I'd just do it. We can talk about it together. Now notice that this one's a little bit different, and you're probably still getting those flashbacks to first year. And I wanted to do this because the eigenvalues are repeated now. So we're not talking about symmetric matrices. We're not talking about, the friendly entry-level problems. This is a little bit more serious. Okay? So, you're given a matrix A. Is it symmetric? No. Okay? Boo-hoo. What do we do when we have repeated eigenvalues? How do we get our eigenvectors? Well, it's not too difficult, but it's something you need to be aware of because we may ask you this question. Okay? So, they've given us a little bit of a head start. So, they're saying that for this eigenvalue, that's the corresponding eigenvector I get. What about the other case? Lambda equals -1. Okay? Well, we've kind of got to produce two things here. We've got to produce two vectors. How do we do that? I'm a little confused. Let's see what we can do here. All right? So consider, please. Okay, it's repeated. Okay, so what we want to do is solve for the corresponding eigenvector V for that value lambda equals -1. Okay? So what are we going to get here? We're going to get a plus I times V equals a 0 vector. All right, so let's go through and solve this. So here's my original matrix A. So A plus I, we're just going to add 1 to the main diagonal. Yep? And then everything else stays the same. Okay, so think back, Math 1131, your first term at university. Great memories. What can I conclude from that system down the bottom? What is it saying? What is the actual information that it's telling me? System of equations. And what about that system? What can you say? What can you say about the rows? They're similar. Yes, we're heading in the right direction. The rows are similar. What else can we say? Building on that. I don't think they are. No, oh, I like it. That's good. If I make a mistake, I'll say the same thing. Row 1. What is the relationship between row 1 and row 3? Huh? Yeah, there's like negative of row 1. And the same with row 2 and row 1. And row 2 and row 3. So what is the actual equation that V1 and V2 and V3 satisfy in this thing? There's only one. There's only one equation. But we've written it out 3 times. So V1 equals V2 plus V3? Does that make sense? Right? So, you know, this is saying negative 4V1 plus 4V2 plus 4V3 equals 0. This one's saying 4V1 minus 4V2 minus 4V3 equals 0. If you just move that around, right, you're going to get something like this. Right? Or yep. Yeah. Okay. So, are we going to get a unique solution for V1 and V2? No. But what we want to do here is be a bit strategic and say, hey, I want 2 eigenvectors out of this. So how am I going to do this? Well, one way is to, you don't have to do this, right? Is to row reduce, right? And I know people are going, oh my God, I hate this. Right, I don't want that. You don't have to do that, right? You don't have to do that. But I'll just show you how you can do it, okay? So, I don't know, why don't we divide the top and, multiply top and bottom by negative 1/4. Okay? And I don't care about the zeros on the end because they're not going to change. Okay, so let's go back to Math 1131. What row operations can I do to make it simpler? Maybe row 2 plus 6 row 1, and row 3 minus 4 row 1. Okay, so what am I going to get? 0, 0, 0, 0, 0, 0. Yep. Okay, so I've gone back to where I started with. So what do I do now? I've forgotten. Right. Well, look for the leading rows and the leading columns. That's a leading column. These ones are not. Okay? So I'm going to introduce two parameters, say mu and lambda. Okay? So this variable is your V2 variable, this is your V3. So I'm going to let V2 equal lambda and V3 equal mu. Okay? So the top line, or this line, will say V1 equals V2 plus V3, lambda plus mu. So we write that all as a column now. V1, V2, V3. All right, almost done. And if you break that up, there are our two eigenvectors. Are they linearly independent? Yeah, you bet they are. So even though we only had one measly eigenvalue, we can get two things to give us what we want. Okay? Yes.
Could we have just not done any of these but used two different variables for our C when we're getting the eigenvalue? Yeah.
Yeah, look, the only reason I'm showing you the row reduction is because you had to suffer it in first year, right? And if you don't like it, don't do it. If you have a better method, do it. Okay? Do it. So, what would our M matrix be? It would be this vector as a column, this vector as a column, and this vector as a column. That's it. That's it. Yeah. Okay? So people get angry or upset or triggered when they have these repeated eigenvalues. You can do it. It's just a bit more work. Okay? Let's take, hello, welcome. You've come just at the right time for the break. Let's take a 10-minute break and we'll come back at 5 past. All right, I hope you've had a break. All right, so what else can you do with matrices? What else? Well, I'm glad you asked. I'm glad you asked. So the last thing I'm going to show you with matrices is how to solve systems of differential equations. Okay, systems of differential equations. So if I say the phrase system of differential equations, do people see that in their other courses? Systems of differential equations, like simultaneous DEs. Yeah, where do you see it? I forgot, but you know the term, right? Yeah. Anyone else? Yeah. In the solids. Yeah. Anyone else? Yes. Classical mechanics. Excellent. All right. So systems of DEs appear in many, many places, right? So they're also good at modeling all sorts of things. Okay? So I don't have anything in the course pack for this, so I thought I'd just do an example from Mobius. I hope that's okay, right? So let's have a look. we're blending matrices with DEs, which is a little bit weird because people go, hang on, I do matrices in algebra, but I do the DEs in calculus. What is going on? You can blend them. You can, bring them together. So this is straight out of Mobius, okay? So let's read the question. Consider the 2 by 2 matrix, M. Okay, is it symmetric? Is it symmetric? 9. It's not symmetric. Okay? It's not symmetric. So we're no longer on the entry-level problem. Okay? But that's not going to stop us. Okay, they want us to do 2 things. Calculate the eigenvalues and enter them in the box below. Okay? So I've done that. And then the second question that they pose to us, hence, solve the following problem. Okay, what does the word hence mean?
Use your previous answer to solve the next one.
Yeah, with the thing above, do something, right? Hence is like an old English word. Right? There's also whence and thence. If you can explain to me what they mean, I would appreciate that. So the first question is pretty easy, right? You just basically solve. So anybody at home, what are your definitions for whence and thence? Tell me all about it. All right, so to get these things, you solve the determinant okay? So you solve that, you get a quadratic, and you get 2 values. Now, even though it's not symmetric, you still get nice values, -1 and +3. And they're not the same. Okay. Hence, solve the problem. All right, so let me show you a cool thing. We're basically looking for a vector that contains 2 functions, x of t and y of t, such that when you differentiate them, they satisfy the simultaneous equations. Now, what's this extra bit on the end? I really think they meant this here. Okay, so they're the initial conditions. It's not exactly clear from the typesetting, but that's what it means. So when t equals 0, x is equal to 7, and when t equals 0, y is equal to 2. Okay? So you've got 2 functions, and they depend on each other. Okay? So what might a model look like that's associated with this system? Okay? Well, one of the standard models is, say, how can I put this? Some sort of symbiotic relationship. Okay, so symbiosis is when 2 things, they depend on each other but in a positive way. Right? So what would be an example of that? You might have you might have, so there's no competition. I'm just trying to think of an example. Just give me a sec. Okay, all right, so according to the Natural History Museum, this sort of symbiotic relationship, okay, try that again. According to my extensive research, these are 2 examples of symbiotic relationships. So you can think of zebras and birds, okay? So the zebra gives the birds food to eat off its back or whatever, or off its neck or whatever. And the birds clean the zebra, right? So the more zebras there are, the more birds there'll be, and the more birds there are, the more zebras there'll be. Okay? So this is similar to the situation that we have here. Right? So think of x as the number of birds and y as the number of zebras at both at time t. As both populations increase, the speed of the rate of the population increase accelerates, right? It goes up. All right, so the question is, how do you solve this problem? How do you solve it? How do you solve it using matrix methods? Well, let me show you. Let me show you. Now, you don't have to do this because it's actually very easy to solve, right? So let's say I've got a general problem. So here's my system. Yeah? So M sum matrix, x is a function of t, y is a function of t, and I want to solve it, right? And you know what this matrix M is. In this case, it's here. All right, so what do? I'm going to make a substitution. So my vector function x is going to be the product of some matrix P with some other vector function y, okay? And what I'm going to do, I'm going to substitute it in to both sides of this equation. Okay, so py dash equals m times p of y. All right, now p is a constant matrix, m is a constant matrix, so when you differentiate here, what are you going to get? You're going to get p times y dash. Okay, so if we rearrange for y dash in the bottom line, so take p inverse to both sides, look what's going to happen. Okay, so who can impress me? What is that going to give you? Yeah. Diagonal matrix, exactly. You guys rule. Okay? Now, diagonal matrices are nice because they're easy to work with. So you can solve this and then get x, the x vector, whatever it is. Okay? Okay, so they're all going to be exponentials. Nice. Okay? So let's go back and solve our problem. Okay, so how do you do this if you're given a problem like this? And this may be in the lab test too, so you obviously don't want to write down all that stuff that I just wrote down. You just want to solve the problem, right? Okay, so what's going to happen here? Right? So if these are my eigenvalues, right, I know okay, so y1 dash equals negative y1. That's what the first row says. So what is the answer to that problem? y1 dash equals negative y1. And the second one says y2 dash equals 3 y2. So what are the solutions to those problems? What's y1 and y2? Yeah, they'll both be exponentials, right? And so y1 will be what? Something like a e to the negative t. And y2, e to the 3t. Okay? So we've solved that. So now to get the full solution, right, we could go back here. And we're going to get x und y. Okay? So what will our P matrix be? How do we get this magical P matrix?
Is it like pretty much each of the columns are the eigenvectors?
Yep, exactly. Right? So here we found the eigenvalues. Didn't find the eigenvectors yet, but let's do that now, right? Okay, so according to my calculations, for this eigenvalue, the eigenvector is something like this. You don't have to normalize them. And for this, it is 1, 2. Okay, so y1's that, y2's that, we're going to get some sort of linear combo of exponentials. Okay, so we can expand that out. And there it is, A and B are constants, right? So we solved the simpler problem with the diagonal, we got exponentials, then we transformed everything back. Okay? All right, so how do we get A and B? A and B you get from this information. Okay, you basically sub in t equals 0 in here, and you set them equal to, what is it, 7 and 2 or something. Okay? Okay? So, I won't do that because it's simultaneous equations, I can't be bothered. But there's an interesting question here. People are already asking in the break, this is too much. Can't you make it simpler? Let me show you something. This is probably something they don't want you to know about. But screw it, I'm going to do it anyway. Okay. Before I do that, questions though. Questions. Questions on the method. Questions at home. No zebras were harmed in the solution of this problem. Questions? Let me show you something else. Let me show you something that I think is pretty cool. The word hence is an interesting one because it's almost like they're giving you an order, right? So if you learn English as a second language or third language, you hear about the imperative, right? The imperative, it's like a command, right? Get out, do this, shut up, learn faster, teach better, right? Hence is kind of like an order. Okay, I don't particularly like orders, do you? Do you like orders? Do you like being bossed around? You tell me. I would think no, right? I would think no. Oh, so do you like orders? Do you like getting people giving you orders? No, me neither, right? Me neither.
What are the assumptions behind this process?
Well, so basically, as long as M is a constant matrix, it works. Right? Yeah. If it wasn't a constant matrix, you'd be in trouble, I reckon. So just with constants in it. But let me show you this. Let me show you what else you can do. Because I don't like taking orders, and you shouldn't either. Right? Watch what happens if I take this and I differentiate. Let's say I differentiate the top one. With respect to t. Yeah? So I take this, I differentiate it. Now, let's have a look here. I've got dy dt there. So maybe I can replace dy dt here with that. Okay, now is it starting to look like something a bit more familiar? Dx squared dt squared equals dx dt plus 4x plus something else. Okay? How can I get rid of that y? Well, y is that minus x. Would you agree? So 2 of those, 3 of those. Okay, hello 1, 2, 3, 1. It's x double dash minus x dash minus 3x equals 0. Huh? Oh. What have I done wrong? Oh, yeah. 2, thank you. 2x dash. But the point is, these systems, and you probably study a lot of systems at university, they're actually things you already know. 1, 2, 3, 1. Okay? So even if you don't like the matrix methods, you can still solve this by just making it a second order problem. Okay? You can do it if you want to. If you want to fight the power and say, no, don't hence me. Right? So, which one's better? They're both good. The second method's good because it's probably familiar. Right? The second equation's familiar. Okay? What do people think at home? Oh, there's only 20 people. Come on, people. Give me something. So, matrices or second order problems? You decide. As if they could, like you're doing an exam, right? How can they tell which method you're using? They can't. Right? They can't. So yeah, so it's up to you. What do people think? What do people think? Like I said earlier, a lot of these problems can be solved by first year. A lot.
So the line x vector equal py, can I see it as a linear transformation of a vector turned into a d?
Yeah, so we transform.
Right.
So we're transforming something. I'm just going to put the aircon back on. We're transforming something, right, into a problem that we can solve. That's where the diagonal matrix comes in, right? We're solving that, and then we're transforming it all back to the original kind of setting. Okay?
So we transform it back to a y, and then say, let's solve one function.
Exactly.
Okay.
Right? Exactly. So this is what we do in mathematics a lot. You've got a problem you don't know how to solve. We simplify or transform the problem. We solve that transformed case, and then we transform everything back. Yeah? Okay. All right. So they're the three main questions that we'll ask you about matrices. One is the symmetric matrices and the quadratic forms. The second one is about eigenvalues and eigenvectors, diagonalization. The third one is a question like this, where you have a system of equations. Okay? Other questions? Other questions? Questions at home? Okay. All right. Okay. So matrices is quite a short topic. Yeah, there aren't that many questions. The questions are very predictable. I think what I'd like to do is to move on to something a bit more challenging, right? So who here's heard of Laplace transforms? Can I have a show of hands? Who's here? Yeah? Has anybody used it? Has anybody used Laplace transforms? Yeah, Fourier stuff? Ah, but you've seen it before. Okay, all right. Anyone else? Anyone at home? Laplace transforms are amazing. You know why? And there's a great segue, because they do exactly the technique that we just discussed. Yeah, you take something, you don't know how to solve it. You transform it to an easier problem. You solve the easier problem and then you transform everything back. If you can understand that, then this is very easy. Okay? All right. So, where does the word Laplace come from? Very famous scientist, mathematician, I think he was an engineer as well, French, and he's famous for these transforms. What we're going to try to do is solve problems like these. Okay? I'm going to jump ahead just for a second to show you what we learn transforms for. Okay? We're going to have differential equations, but with some things like pulse functions, jump functions, switching functions, those sort of things. Okay, that's what that U is. Okay. Now, if you go back to first year techniques, you probably can solve it, but it's not as streamlined, it's not as fast. Okay. So, what is a Laplace transform? Well, I'm glad you asked. Here it is. Okay? So you start with a function of t, let's say, little f. And you take that function and you multiply it by an exponential called the kernel. Okay? And then you integrate the product over the half line with respect to t. Okay? So there's a whole bunch of notation that you can use for this. We use curly L or we use capital F. Okay? So note that because we're integrating in this sense with respect to t, and there's an s in there, the whole thing will actually be a function of s. All right? Now, what does this have to do with differential equations, I hear you saying? I hear you asking. Okay. So let me try to give you a little bit of insight. Differential equations involve derivatives, right? And integrals, they're the opposite of derivatives. So when we're transforming differential equations, we're kind of using this to undo the derivatives. Okay, we solve whatever problem we get and then we transform everything back. That is the main purpose of these Laplace transforms. Okay? So you would expect somehow to have an integral in there if you're dealing with derivatives, because they kind of undo differentiation. But we'll see that later. But let's just do one of these problems and calculate a transform. Okay. So yeah. So here is an example. They're asking us to take the Laplace transform of the function e to the negative 2t. So let's try it and see what happens. Now, believe it or not, you're not going to actually do many integrations when you do this. I'll show you why in a minute. But let's just do it and see what happens. Okay? All right. So we take e to the negative 2, we shove it in there, and then we want to integrate it. E to the negative 2t. Okay, so remember back to Math 1131. This is what's called an improper integral because it's got an infinity sign in the integral sign. Okay, so we can deal with those, but we just need to remember how to. Okay, so that's an S, and that's a 2. All right, so let's just do what any normal person would do and combine the parts. Okay, so it looks like we're integrating an exponential with respect to t. In this case, we would hold s constant and manage that infinity sign somehow. Now, if we're being very proper with our improper integral, we would write it as a limit. You don't have to do that, but I'm just showing you how it works. Okay, so what now? Well, let's integrate this. And the last thing we'll do is take the limit. All right, so we're integrating exponential with respect to t. This is constant. So it'll be something like that. Yeah? So we'll put in our values for t equals b, t equals 0, and then we'll take a limit. Okay? All right, so replace t with b. And same there, so e to the 0 is going to give 1. Okay. Now, in our original problem, we were told that s is greater than 2. So this thing here is going to be positive, so negative, and so the exponent here is going to be negative overall. Okay. So if we take the limit of, what's the limit of the first one going to be? 0. And the limit of the second one, well, there's no b in it, so it just stays the same. Okay? So it's not super exciting. We did an integration and took a limit, and we got some function of s. Great! Okay? So it really does give you a function of s. The integration wasn't too hard, and we just had to work out something to do with the limit. Okay? All right. So then in part 2, there's a bit more of a conjecture. If a is a constant, use 1 to make a conjecture about the Laplace transform of e to the negative at. Okay? So if that is that, what do you think this limit's going to be? Anyone want to have a guess? What's the Laplace transform of? Yep. 1 over S minus A. Okay, you can prove that if you want to. Okay. Yes. Oh, mine. No? What did I forget? Oh, yeah. Okay, thank you. So what I've got is correct, but we'll answer the question properly, exactly. Yeah. Happy? Yeah. All right. Now, I said to you before, don't worry, don't stress. You won't be doing too much integration. Does anybody know why? There is a pattern. Yeah. But there's something even better than a pattern. Bum, bum, bum. Yeah. So, this is called a table of transforms. Have you heard of this? Do you know of this? Right. Basically, down the left-hand side, you've got your original function. Down the right-hand side, you've got the transform. Now, it astonishes me every time I teach this course. And I've taught this course a lot, but not recently, right? Students still can't use a table. Okay? Students still can't use a table. It's something that's not a diss. Okay? I'm not disrespecting anybody here. What you need to do is just get familiar with working with a table. Okay? It's much faster than doing the calculations, trust me. Okay? Yes?
Will we have the table?
Excellent question. Yes, you will have the table. Okay. You will have the table. The table is almost identical to this. It's on Moodle if you want to go have a look at it.
This table's on the formula sheet, but the formula sheet wasn't available in lab test 1.
No, for the final. For the final exam. This will not be on the lab test 2, how you say. Yeah. Okay, because lab test 2, what's on lab test 2? Weeks 4, 5, and 6. Topics 4, 5, and 6. So ODEs, double integrals, and matrices. Yeah. So this will not be on lab test 2. Will not be on lab test 2. So we're going to play a game with the table in a minute.
What is the Laplace transform like actually doing? Like, how would you visualize what you're doing here?
The best visualization I can give you is that you're going between two worlds, right? You're transforming something into another space of functions involving S, right? You solve for that, and then you've got something on the right-hand table, you match it up with what you've got on the left-hand table. So you're inverse transforming. So you're going somewhere, sorting it all out, and then you're getting back through an inverse transform. Okay? So again, it comes back to what I was saying before, right? Well, it's a function. It's a function space, right? It'll the hard part is getting back as well. So, to get back, you have to know sort of complex variables and all sorts of stuff, which is way beyond what we're doing, right? Which is kind of why we're using tables, really. Yeah. But I think of it as at a meta level, right? We've got something we want to solve. We don't know how to solve it. Make it easier. Solve the easier bit. Get back to where you started. That's pretty much it. I mean, and so what are we doing? We're multiplying by an exponential and we're integrating over a half line. That's what we're doing. All right. So let's play a little game. Everyone, you can play at home too. All right. Down the left-hand side, we've got the original functions of t. Down the right-hand side, we've got their transforms. All right, so if I give you something like this, t squared, What is the Laplace transform of t squared? Who thinks they know? Yes.
Would it be 2 factorial over s cubed?
Yes. And what's 2 factorial? 2, exactly. Right? Okay. What about the Laplace transform of 2? Actually, no, let's be dangerous. 3. The Laplace transform of 3. Who can tell me? Just shout it out. No. 3 over s. 3 over s. Close. Close. Okay? So, you know, because it's an integral transform, if you have like a 3 here, you can pull the 3 out the front. So you multiply 3 by the original one, right? Okay. Okay, we've done that one. Okay, what about the transform of sine of 4t? Not 40, 4t. Yeah, so you go across 4 over s squared plus 4 squared. Yeah, perfect. Okay, now, how would you verify all these things? How would you verify? Well, you can go to your transform definition, put your function in there, and then integrate. Okay? But it's not much fun, and sometimes you need to integrate by parts. Not just once, not twice, but thrice. Yeah, you don't want that. You don't want that. Okay? So, get to know this table. It's like a formula sheet. Use it. Okay? Don't wait till the night before to understand how to use it. Because it's just too much of a risk. Right? Too much of a risk. Now, if you look down the bottom of the table, it starts to get a bit scary. Let's have a look. Here we've got a u function. What is this u function? U of t minus c. So there's this function here. There's that. There's that. Oh my God, there's that. And then there's all these derivatives. Now, this is where we're getting into the actual heart of why these Laplace transforms exist. Okay? This is why Laplace transforms are helpful, because they take derivatives and they undo the derivative. Okay? See how there's no derivatives in, well, that's okay. See how there's no derivatives in these things? That allows us to solve in this transform space. We don't have to worry about derivatives anymore. Derivatives are gone. Okay? But let's get back to this u function. Okay, let's have a look down the bottom. U is 0 for t less than 0. It's a half there, and it's... Okay, so let's see if we can do a picture. Okay, so it's 0 here. Yeah. It's half there. And it's 1 there. Okay? This is a very famous function. Does anybody know its name? Hmm? No, it doesn't have to do with absolute value. Yep. Ooh. Heaviside function. Yes. What do you know about the heaviside function? You know its name. right? Yeah, that's good, that's good. So think of it as a switch, right? It's off and then you flick the switch and it jumps up and it turns on, right? So it's like an impulsive function. It's not continuous, right? It's not a continuous function. It's a discontinuous function, okay? So people talk about it as a switching function. You can switch things off, switch things on. Why do they have this half value? The half value here is sort of halfway between that point and that point, right? It's actually not important. From an integration point of view, nobody cares. But you have a little bit of sort of symmetry if you put the half in. Okay, it's not going to change anything if you leave it out. Okay? All right, so you know how to calculate a Laplace transform. The reason why they're important is to solve differential equations, which we'll get to. And probably the most important thing today in this second lecture is using the table, getting acquainted with the table and not having to do integration all the time. All right, I'll leave it there. If people have questions, come on down. Thanks for staying with me, and we will see you tomorrow maybe.